Hey guys, today we're going to learn how to graph a rational function. In our previous lesson, we learned how to get all the information that we could from the equation of a rational function. Now we're going to put all of that information on a graph. So here's a general guideline of how to graph a rational function. First, we are going to find all of the asymptotes of the function, both vertical and horizontal. Upon inspection of my equation, the degree of the numerator is the same as the degree of the denominator. Therefore, I'm going to divide the coefficients attached to those x's. 2 divided by 1, that is where I have my horizontal asymptote. So we have one at y is equal to 2. Next, we would have to factor in order to find the vertical asymptotes. Since this particular function cannot be factored, I can look at my denominator, and I have a vertical asymptote at x is equal to 1, since that's what would make this denominator equal to 0. I'm going to go ahead and already put that on my graph. So even though asymptotes are invisible lines that we can't see, we're still going to draw them in so that way it makes it easier for us to graph. So we have the horizontal at y is equal to 2, and we have the vertical at x is equal to 1. Next, we're going to find any holes when applicable. Since nothing ended up canceling, there are no holes. So we can move on to step 3. Step 3 is to plot at least one point between and beyond each vertical asymptote to note where the function lies. So here's my vertical asymptote. I'm going to create a table of values using some x's that are on either side of the vertical asymptote, and then plugging in those x's. Since my vertical asymptote is at x is equal to 1, I'm going to plot 0 and 2. You can plot any number you'd like, but I normally like to choose 1x to the left of the asymptote and 1x to the right. You always want to do both sides so that you can see where the graph is going to lie. If I plug in 0, 2 times 0 is 0, minus 1 is negative 1, over 0 minus 1 is negative 1. And negative 1 divided by negative 1 is 1. So we have a coordinate at 0, 1. Next, I'm going to plug in 2. 2 times 2 is 4, minus 1 is 3. And 2 minus 1 is 1. And 3 over 1 is 3. So we have another coordinate at 2, 3. So these are my 2 points. I'm going to go ahead and put that on my graph, 0, 1, and 2, 3. We don't really need too many more points, simply because our graph is not going to be 100% exact, but it's going to show the general behavior of our rational function. So since these asymptotes are going to block our graph, that means that if this point is here, my graph is going to come down like that, never touching the horizontal and above and going above, and never crossing this vertical. So it's got a curve like this. Oops. And then since this point is up here, it's going to be above the horizontal and to the right of the vertical, so it's going to curve this way. And this would be my rational function. Let's try a couple more examples. Here we're going to graph the rational function, and then we're also going to state the domain and range. So before I begin, I'd like to look to see where I have a horizontal asymptote. Since the degree is smaller in the numerator than in the denominator, this means that I have a horizontal asymptote at y is equal to 0. To get my vertical, I'm going to go ahead and factor my rational function. So f of x is going to equal to, in the numerator, I can take out a negative 3, which will leave me with x plus 2. And in the denominator, I can factor that to be x plus 2, x minus 1. Here my x's cancel, so I know I'm going to have a hole. And so my simplified rational function is negative 3 over x minus 1. By looking at my denominator, I can tell that I will have a vertical asymptote at x is equal to 1. So I'm going to put my asymptotes now on the graph. So I have the horizontal at y is equal to 0, and my vertical at x is equal to 1. Now I also have a hole. So let's go ahead and find that hole. Since x plus 2 canceled, this means that my x value of the hole is at x is equal to -2. I'm going to take the -2 and plug it into my function so I can get the y value of the hole. And that's going to be -3 over -2 minus 1, which is -3 over -3. So I have a hole with the y value of 1. So my coordinate is going to be -3, 1. When I put this on the graph, we're going to go to -3, 1, and instead of putting a solid circle, I'm going to put an open circle. So I already know now that on this side of my graph, my function is going to be up here because it's got to go, it connects with the actual graph, but it's just an empty dot. So when I create now my table of values, I have my column here for my x, and this column here, I'm going to use my simplified rational function so it's easier for me to plug in a number. I don't need to choose a point to the left of the vertical because I have the hole there that kind of counts as my point. So I'm just going to choose a point to the right. So since this is at 1, I'm going to choose 2. And I'm going to plug into here into my equation. So -3 over 2 minus 1, which is going to give me -3 over 1, which is -3. So I have a coordinate at 2, -3. I'm going to put that on my graph. And this is a solid circle because that's an actual coordinate. Now that I have my 2 points, I can create my graph. So this graph is going to go like this because those asymptotes, remember, block. And see how I connected it to the hole and then continued onto the other side. And then this way is going to go like this, again, because of that vertical asymptote and the horizontal. So now for my domain. You can now use your graph to help you write the domain instead of using number lines. Although if you do prefer using number lines, you absolutely can. If I read my graph from left to right, I have here it starts at -infinity until my hole. I'm going to have to stop here because of that open circle, which is at -3. I'm going to continue from -3, and then I have to stop at the vertical asymptote, which is at 1. And then the rest of the time on the right side, it goes on forever to the right, so it goes from 1 to infinity. Now for the range. The range is going to be from -infinity, since the graph does go down forever. So now I'm reading my graph from the bottom up. I'm going to have to stop at my horizontal asymptote, which is at 0. Continuing on from 0, I have to stop at the hole, which is at 1. And then it does go up forever after that, so it'll go 1 to infinity. So this would be my graph and my domain and range. Now let's look at some special instances of multiple vertical asymptotes. So here, we're still going to go through our steps on how to graph this particular function by finding horizontal asymptotes, vertical asymptotes, and any possible holes. Let's look at this first one here. You'll notice that the degree of the numerator is the same as the degree of the denominator. So when we divide those coefficients, that means that we have a horizontal asymptote at y is equal to 1. To get any vertical asymptotes or holes, I'm going to have to factor. So this is x squared over, and then this is a difference of squares, so x plus 2, x minus 2. We have no holes since nothing cancels, so therefore we have 2 vertical asymptotes, which are at x is equal to -2 and 2. I'm going to go ahead and put that on my graph. So y is equal to 1, and then x is equal to -2 and +2. I'm going to create a table of values. So here's x, and then here we can either use the regular version or the factored version. That's completely up to you. I'm just going to use the one here. Since nothing canceled, it does not matter which one you use. It's not going to make anything any easier. So I'll do this one using the regular, and then this one I'll use the factored version. So then this is x squared over x squared minus 4. Now when we have two vertical asymptotes, we know that a horizontal asymptote is going to block your graph from going across from it. However, that's only for the ends. When it comes to the middle, if you have two vertical asymptotes, your graph can cross the horizontal asymptote. The horizontal asymptote only really affects the end behavior, but that does not necessarily mean that it's going to affect the middle. So when we are picking our points, we're going to still pick one to the left of the vertical asymptote over here. Since this is -2, I'm going to do -3. But when it comes to the middle section, I'm going to choose several, just so that I can see whether it's going to cross or not. So I'm going to choose -1, 0, and 1. Then for this side, my horizontal asymptote will block my graph because it is at the end. So I'm going to just choose 1, which will be 3. So we're going to plug in our points now. -3 squared is 9. Over -3 squared, 9 again, minus 4 is 5. So we have a coordinate at -3 and 9 over 5. Now if I plug in -1, -1 squared is 1. -1 squared again is 1 minus 4 is -3. So this means that we have a coordinate at -1 and -1/3. Now if I choose 0, 0 squared is 0, and then 0 minus 4 is going to be -4, but 0 divided by anything is 0. So we have a coordinate at 0, 0. When I plug in 1, this will be 1 over 1 minus 4, which is -3. We have another coordinate at 1 and -1/3. And then for 3, this will be 9 over 9 minus 4, which is 5. So we have our final coordinate at 3, 9 over 5. So now let's put all of these coordinates on the graph and see what that's going to look like. -3 and 9 over 5. 9 over 5 is more than 1, almost 2. So it's going to be somewhere around here. So we're just estimating. So that means that on this side of the graph, it's going to do this motion because that vertical asymptote never crosses, and then your horizontal at the ends never cross. For -1, we have -1 and -1/3. So here's -1, -1/3, it's about right here. Then we have 0, 0, and then we have 1, -1/3, so it comes back down. So in this section, you see how it's going up and then it comes back down. It's not going to necessarily cross, so it's going to look like a parabola in the middle. Then for our final point, we have 3 and 9 over 5. So here's 3, 9 over 5 is almost 2, so around right here, and so our graph would come through like that. So here, my horizontal asymptote does affect both the ends and the middle. So something important to distinguish, your horizontal asymptotes, like I said, does affect your end behavior, but not necessarily the middle. It may cross the horizontal, sometimes it doesn't, like in this case. But with vertical asymptotes, your graph never, absolutely never crosses those vertical asymptotes. So at least you always have that. Now let's go to this one here. We have x plus 1 over x squared plus x minus 6. Based on the degrees of my function, since it's smaller on the top than on the bottom, this means that I have a horizontal asymptote at y is equal to 0. Next, I'm going to factor to see if I have any vertical asymptotes. So x plus 1 over x squared plus x minus 6 can be factored as x plus 3, x minus 2. So here I have my two vertical asymptotes, which are at x is equal to negative 3 and x is equal to positive 2. So I'm going to put those on my graph. Here's y is equal to 0, and then x is equal to negative 3, and x is equal to 2. I'm going to create my table of values. So here's x, and this time I'll use my factored version just to see if it's any easier, and you can also decide what method you prefer. So here I'll use the x plus 1 over the x plus 3, x minus 2. So now when it comes to choosing my x's, on this left side, I'm going to choose negative 4. I only need 1 for the ends. For this middle section, I'm going to choose at least 3. So let's do negative 1, 0, and 1 again, just because those are easy to plug in. And then for the right side of 2, I'm going to choose 3. So we're going to plug these in. Negative 4 plus 1 is negative 3, over negative 4 plus 1 is negative 1, times negative 4 minus 2 is negative 6. So we get here negative 3 over positive 6, and so that gives me the coordinate negative 4, negative 3 over 6 can be simplified to 1/2. Now when I plug in negative 1, negative 1 plus 1 is 0. And I don't really need to plug it into the bottom because 0 divided by anything is going to be 0. So my other coordinate would be negative 1, 0. Now let's plug in 0. 0 plus 1 is 1. Over 0 plus 3 is 3, times 0 minus 2 is negative 2. So I have a coordinate at 0, negative 1 over 6. When I plug in 1, 1 plus 1 is 2, over 2 plus 3 is 5, and then 2, oops, I plugged in 2, not 1. Let's erase that. Excuse me. 1 plus 3 is 4, and 1 minus 2 is negative 1. So this is 2 over negative 4. That means that I have a coordinate at 1, and then 2 over negative 4 can be simplified as negative 1/2. When I plug in my final point, 3, 3 plus 1 is 4, over 3 plus 3 is 6, times 3 minus 2 is 1. So 6 times 1 is 6. So we have our final coordinate at 3, and then 4 over 6 can be simplified to 2/3. So these are my points. I'm going to go ahead now and put them on my graph and see what happens. We have negative 4 and negative 1/2, which is down here. So I know that my graph is going to do this. Then I have negative 1, 0. So you can see at negative 1, 0, it's already touching the horizontal asymptote. So what that means is that it is going to cross. Then we have 0, negative 1, 6, which is about right here. And then 1, negative 1/2, which is a little lower. You can see that we have like it almost looks like a line. But because of these vertical asymptotes, since it's never going to cross, this is going to get closer to it, but then it's going to have to drop down. And then on this side, we're going to go up, but then it's going to have to come up like this. And then for our final point, we have 3 and 2/3. 2/3 is a little bit less than 1, so right about here. So that means that this side of the graph is going to curve this way. So you have two cases of horizontal asymptotes when you have multiple verticals. Here, when it doesn't cross, it ends up looking like a parabola. But here, when it does cross, this middle section almost looks like the cubic function since it's got that elongated S look. So when you have multiple verticals, always test multiple points for the middle section so you can double check whether it's going to cross the horizontal or not. Now, something that we did not discuss before is the presence of any slanted asymptotes, also called an oblique asymptote. Now, if there is a slant asymptote, you will have no horizontal asymptote, and the degree of the numerator is exactly 1 degree larger than the denominator. That's how you know you're going to have a slant. If that's the case, then you're going to have to figure out what the equation of the slant asymptote is. So let's look at how we do that. As you can see from this equation, we have x squared plus 1 over x minus 1. And I'm already giving you the graph of what that looks like so that you can see how the slant is found. The degree of the numerator is exactly 1 larger than the degree of the denominator since this is 1. So that automatically means, since the degree is larger, that there is no horizontal asymptote. And then once I figure that out, I check to make sure if the degree on top is 1 larger than the bottom, which it is. And how you find the slant is this represents division, so we're going to divide. And to make things easier, you can divide using synthetic division. So what it is x squared plus 1 divided by x minus 1. Whatever the denominator is equal to 0, that's what you're going to put in your box. So we would have to add the 1, so in the box would go 1. And in the numerator, we have the x squared plus 1, so I'm going to put 1, there is no x, so 0, and 1. Bring down the 1, 1 times 1 is 1, 0 plus 1 is 1, times 1 is 1, and then we get a remainder of 2. When you're finding the slant, the remainder does not matter. This is going to be the equation of the slant. Since the original is x squared, then that means that the slant is going to be 1x, so x plus 1. If I draw that out, here's my y-intercept, which is 1, right? Because this is mx plus b, so this is my y-intercept. My slope is 1, so that means I'm going to go up 1, right 1. Up 1, right 1. And I'm going to do this going across so you can see how the graph gets really, really close to that line, but it never actually touches it. So that's how you would find your slant. Once you have your slant, and then here's my vertical asymptote at x is equal to 1, you can see how the graph kind of sits in what I call the pockets of the slant and the vertical asymptote. So now let's try that out with a problem. Now in this question here, we're not going to actually graph the rational function. We already have it graphed here. We're just going to see how we get all of the information from the equation so that we can verify that this is indeed the graph. So first off, to figure out if we have a horizontal asymptote, we're going to compare the degree of the numerator with that of the denominator. I can see that there are none, that the numerator is larger than the denominator, therefore there is no horizontal asymptote. And once you have that there is no horizontal asymptote, then we're going to verify if we have a slant, which would mean that the degree of the numerator is exactly 1 larger than the degree of the denominator, which here it is. So I can find the equation of that slant by setting the denominator equal to 0, and I get that x is equal to 2. So that's what I'm going to put in my box. And in the numerator, we're going to put, going across here, we're going to put all of the coefficients of the numerator. So that'll be 1, -5, and 7. Bring down the 1. 1 times 2 is 2. -5 plus 2 is -3. Times 2 is -6. And 7 minus 6 is 1, but the remainder, remember, does not necessarily matter. This is going to be the equation of my slant asymptote. So the equation is going to be y is equal to, this is 1x minus 3. Additionally, if I wanted to find if there was, the equation of the vertical asymptote, first I would need to see if any factors of the numerator would cancel with that of the denominator. Obviously, you can see from the graph that we do have a vertical asymptote, but let's just verify as to why. This numerator, if I try to factor, we would need to find the two numbers that multiply to give you 7 and add to give you -5. But the only two numbers that multiply to give you 7 are 1 and 7, or -1 and -7. Neither of these add up to give you -5. So that particular numerator cannot be factored. Therefore, we do have a vertical asymptote at x is equal to 2. So let's look at this graph here. If I put x is equal to 2, my vertical, you can see that the graph never touches that vertical asymptote. And now let's draw in x minus 3. -3 being the y-intercept, so I'm going to go down 3. And the slope here is 1, so I'm going to go up 1, right 1. And I'm just going to go all the way through my graph so we can see how it gets really, really close to that slant. But again, it never actually touches the slant. And then that's where you have your graph. Now, your graph, just as a side note, we can see here that the function is within those pockets between the vertical and the slant. However, we don't necessarily know if it's going to be in here, or it could also be out here, outside of the asymptotes. And how we would tell is we would still create our table of values and plot a number to the left and to the right of the vertical, and then see where it lands. If it lands within the pocket, then we know it's going to look like this. If it lands outside, then it's going to look more like an X, like that. So those are your two graphs of rational functions with a slant. It could either look like the one in black, or it could look like the one in pink. So now let's put everything together, and we're going to find the domain of these rational functions here. So let's look at this first equation. We have f of x is equal to x squared plus 3x minus 3. So first off, I noticed that we have no horizontal asymptote because the degree of the numerator is larger than the degree of the denominator. And if there's no horizontal asymptote, we're going to see if there's a slant. The degree of the numerator is 2 and of the denominator is 1. 2 is exactly 1 larger than 1, so for sure there's going to be a slant. So we're going to figure out what that slant is. If x plus 1 is equal to 0, that means that -1 is going to go in my box. And going across would be 1, 3, and -3. Bring down the 1. 1 times -1 is -1. 3 minus 1 is 2. 2 times -1 is -2. And we get a remainder of -5. Not that it matters. So the equation of my slant is going to be y equals 1x plus 2. Now I also want to see if I have a vertical asymptote. We're going to look at the numerator and see if there's any way that I can factor that. The only two numbers that multiply to give you -3 are either 3 and -1, or -3 and +1. Again, neither of which add up to give me 3, so this numerator cannot be factored. So that means that I do have a vertical asymptote, which would be at x is equal to -1. So I'm going to put my asymptotes now on this graph. So we have the vertical at x is equal to -1, and then we have the slant at x plus 2. So 2 being the y-intercept, which is right here. And then I'm going to go up 1, right 1, because my slope is 1. So I'm just going to extend that all the way across the graph. Now I want to see whether my graph is going to land within the pockets or here on the outside. So I'm going to go ahead and create my table of values. So here this is the x squared plus 3x minus 3 over x plus 1. Since my vertical asymptote is at -1, I am going to choose to plot x is -2 and x is 0. If I plug in -2, -2 squared is 4, plus 3 times -2 is -6, minus 3 over -2 plus 1 is -1. 4 minus 6 is -2, minus 3 is -5, and -5 over -1 is 5. So I have a coordinate at -2, 5. Now if I plug in 0, 0 squared is 0, plus 3 times 0 is 0, minus 3 would be -3, over 0 plus 1 is 1, and -3 over 1 is -3. So we have a coordinate at 0, -3. I'm going to plot these 2 points now. We have -2, 5, and then we have 0, -3. As you can see, it is outside of my pocket, so we're just going to hug those asymptotes. So this graph is going to come down like this, and then it's going to get really close to that slant, but never actually touch. And the same thing on this side. It's pretty much hugging the vertical, and then it's going to go close to the slant. And this is what my graph would look like. Now for my domain. The only restricted value for my domain is where you have that vertical asymptote. So something to keep in mind when you're finding domain and range, the only time that you have to worry about excluded values are when you have any asymptotes and holes. Your domain is affected by the vertical asymptote and the x value of the holes. As you can see here, the slant is not going to affect my x's, since my graph still goes forever left and close to the vertical, and then it still goes forever right and close to the vertical. So my domain is only restricted by x is equal to -1, making it -infinity to -1, u -1 to infinity. Typically, when we have a slant, I'm not going to ask you too often what the range is, simply because it does get a little bit complicated, like here in this problem, where if I erase these here just so we can focus on the graph that's given, you can see that there's a gap here within the range. Like these y values would not be included, and I'm not going to expect you to figure out what those values are. So whenever we have a slant, I'm just going to ask you for the domain. However, for this one, if I did want to find the range, these are a little bit easier when it's not inside of the pocket, because it does go up forever and it does go down forever. So the range here would be -infinity to infinity. Let's look at one final problem. So first, to keep with tradition, let's figure out if we have any horizontal asymptotes. The degree of the numerator is 2 and the degree of the denominator is also 2. So that means that we do have a horizontal asymptote, which would be when we divide the coefficients. And even though I don't see them, I know that this is a 1 and this is a 1. So 1 divided by 1 is 1. So we have a horizontal asymptote at y is equal to 1. And since we have a horizontal asymptote, that means that we cannot have a slant. These two cannot exist at the same time, so either you have one or the other. Now, moving on to get if there's any wholes or vertical asymptotes, we're going to need to factor everything completely. So I'm going to go ahead and factor x squared plus x minus 2, which would give me, minus 12, x plus 4, x minus 3. In the denominator, x squared plus 2x minus 8 can be factored as x plus 4, x minus 2. Here, the x plus 4's would cancel, and so we're left with a simplified rational function of x minus 3 over x minus 2. Since I canceled, that means that I do have a whole, and the x value of my whole would be at negative 4. To get the y value, we're going to go ahead and plug everything in. So we're going to find f of negative 4. And remember, we plug that into the simplified version. So negative 4 minus 3 over negative 4 minus 2. Negative 4 minus 3 is negative 7. And negative 4 minus 2 is negative 6. Negative 7 over negative 6, those negatives will cancel, leaving me with 7 over 6. And that is the y value of my whole. We also have a vertical asymptote, since we still have a factor left over in the denominator. So that means that I have a vertical asymptote when that denominator is 0, which is at x is equal to 2. So I'm going to go ahead and put everything that I've gotten so far into my graph. So I have the horizontal at y is equal to 1. I have a whole at negative 4 and 7 over 6. 7 over 6 is a little bit more than 1, so I'm just going to put a little hole right above that asymptote. And then I have my vertical at x is equal to 2. Next, I'm going to create my table. I'm going to use my simplified rational function to figure out my values. And I'm going to pick a point to the left and a point to the right of my vertical. I don't need to necessarily pick a point to the left. Since I see where my whole lands, it's above the horizontal. So I know that for this side of my graph, my function is going to be above the horizontal and going to curve along those asymptotes. But for the right side, I'm going to choose 3. So now we're going to plug that in. 3 minus 3 is 0 over 3 minus 2, which is 1, and 0 divided by anything is 0. So I have a coordinate at 3, 0. So I'm going to put 3, 0. This is a solid circle because it is a value. So that means that my graph is going to curve along the asymptotes here. So now, to get the domain, and I forgot here to put the range, so we're going to do both. The domain is restricted by the vertical asymptote and the x value of the whole. So you can do it however you like, either using the graph or using what we did in the previous lesson by creating your number line. The only two excluded values are negative 4 and 2, and if you look at my graph and I read it from left to right, this would be from negative infinity until the value of the whole, which is negative 4, u, negative 4, until we get to the asymptote, which is at 2, u, and then the rest of the graph to the right of the asymptote, which is 2 to infinity. Now for the range is restricted by the horizontal asymptote and the y value of the whole. So if I work my way from the bottom up, my range would start from negative infinity until 0, u 0 until the value of my whole, because that is above 0, which is 7 over 6, u 7 over 6 to infinity. And that's how you put all of the information that we've done before for rational functions onto a graph.